An electronic circuit is made up of various components. These can be classified into passive elements and active elements. Let's begin by taking a look at passive elements. Most substances exhibit what is known as electrical resistance. Resistors are elements within a circuit that take advantage of the characteristics of electrical resistance. Resistors are used to control electric current and to convert current signals to voltage signals. Resistors come in various shapes, sizes, and materials, depending on their use. Furthermore, some are fixed resistors with a fixed value of resistance, while others are variable resistors whose resistance value can be altered. Fixed resistors are denoted on the electrical circuit like this, and variable resistors are expressed like this. Some resistors are color-coded to indicate their resistance value. Color codes can be used to calculate resistance value. Now let us explain how to read color codes. A numerical value is assigned beforehand to each color. Color codes can be printed for any terminal. The fourth color band indicates resistance error. The value of resistance can be determined by applying color code values to a prescribed formula. This carbon film resistor, for example, has yellow, purple, red, and gold color bands, arranged in order from left to right. Their corresponding values are 4, 7, 2, and 5. From these numbers, we can determine that the resistance value is 4.7 kiloohms and the error is plus or minus 5%. The illustration here is an electrical circuit comprising a battery, switch, and resistor. This circuit can be shown with a circuit diagram like this. When the switch is turned on, voltage E is applied to resistor R and current I flows. This relationship is known as Ohm's law. For example, if voltage E is 100 volts and resistor R is 100 ohms, the current I is 1 amp. If you wish to control the current to 0.5 amps, then R should be 200 ohms. Controlling the current is one of the functions of the resistor. We can also deduce that voltage of 100 volts is generated between the resistor terminals when a current of 1 amp is passed through a resistor of 100 ohms. For example, resistance of 100 ohms will be used to convert current of 0.1 amps into 100 volts. Heat is generated when current flows through the resistor. This means that the resistor consumes electric power. The formula P equals E times I is derived when the voltage of the resistance is considered as E, current as I, and electric power as P. If Ohm's law is substituted here, we obtain the formula P equals I squared times R, or P equals E squared over R. Thus, as electric current increases, power consumption increases. As a result, the resistor's temperature rises due to heat generation. This means that the resistor will burn if the current is too strong. As such, each resistor has a value for maximum allowable electric power. When resistors with high power consumption are cooled for, products that can control heat generation by means of forced air cooling or water cooling may be used. A capacitor is an element used to temporarily store the electric charge. Capacitors are used for a variety of applications. Even a small electronic device like a mobile phone uses nearly 100 capacitors. Among the uses of capacitors are Temporary storage of electrical energy. AC and DC separation and selection. Phase shift between voltage and current. And signal differentiation and integration. While external appearance and structure may vary from capacitor to capacitor, the basic structure can be represented by a pair of electrodes. When voltage is applied between these electrodes, the electric charge accumulates on the surface of the electrodes. The larger the surface area of the electrodes, the larger the amount of electric charge that can be stored. The narrower the distance between the electrodes, the larger the amount of electric charge that can be stored. The amount of storable electric charge can be increased by inserting an insulator, known as a dielectric, between the electrodes. The characteristics of capacitors differ according to the type of dielectric used, making it possible to employ capacitors for a variety of applications. Some capacitors have no polarity. Others do have polarity. The capacitors shown here are in common use. They represent a small proportion of all capacitors. Regardless of polarity, capacitors are indicated like this in electrical circuit diagrams. An exception is the electrolytic capacitor, which is indicated like this to differentiate it from the other capacitors. When voltage E is applied between the terminals of a capacitor, a proportional electric charge Q is stored in the capacitor. The proportion coefficient C is known as electrostatic capacitance. The following formula is obtained. Q, electric charge, equals C, electrostatic capacitance, times E, voltage. Aluminium electrolytic capacitors offer high capacitance at a low price, leading to their frequent use for applications wherein the voltage of the electrical circuit board must be kept constant. Compared to other capacitors, however, they have a relatively short useful life, about 7 to 8 years on average. This does not mean that they cannot be used after 7 or 8 years. It means that electronic devices that use aluminium electrolytic capacitors may begin to generate heat or emit noise as they age. Using the aluminium electrolytic capacitor in a cool environment lengthens its useful life. Research indicates that useful life can be doubled by reducing the ambient temperature by 10 degrees Celsius and trebled by a reduction of 20 degrees. On any electronic circuit board, numerous aluminium electrolytic capacitors are used. The lifespan of these electronic circuit boards is generally determined by the lifespan of the aluminium electrolytic capacitors. A spare electronic circuit board is provided on board ships in case the board in use breaks. This spare electronic circuit board must be placed in a cool place to ensure that it can be used over an extended period of time. However, the electronic circuit board may become rusty if this cool place is humid. To prevent rusting, an electronic circuit board can be stored in a plastic bag, along with a dehumidifying agent. An inductor is a circuit component comprising a coil of conductive material wound around a core. Inductors temporarily store magnetic energy. Although capacitors are more common, several inductors can usually be found on an electronic circuit board. Functions of the inductor include temporary storage of energy, AC and DC separation and selection, phase shift between voltage and current, and magnetic field generation. While inductors vary in terms of external appearance and construction, the fundamental design is that of a core with a conducting wire wound around it. Inductors are classified by shape, of which there are two types, solenoid and pancake. Inductors used on electronic circuit boards are mostly of the solenoid coil type. A greater amount of magnetic energy can be stored when the solenoid coil is wrapped around a ferromagnetic core. The core itself can take a variety of shapes, depending on the application and voltage current. The larger the current that passes through the coil, the more magnetic energy is stored in the inductor. This characteristic varies depending on the number of loops in the coil, the shape of the core, and so on. The functional characteristic of the inductor is known as inductance and is expressed in units of H, Henry. Some electrical equipment generates electrical noise, known as noise. If precision equipment like a temperature measuring device is electrically connected to electrical equipment generating noise, it may not function properly. To avoid this problem, an inductor may be used as a noise filter. Compared to resistors and capacitors, inductors are less susceptible to damage. When they are damaged, it is often difficult to detect from external appearance alone. Insulation film applied to the coil will deteriorate in environments with high ambient temperatures. In the worst case, the coil short-circuits and is no longer capable of functioning as an inductor. Coils are found in the motors of seawater and freshwater pumps, and their insulation is weakened by the absorption of moisture. The main purpose of measuring insulation resistance using a mega is to check for coil insulation degradation. The transformer has a structure featuring two or more coils sharing one core. Magnetic energy generated in one coil is transmitted to the other coil through the core. The main functions of the transformer are to increase or decrease AC voltage and AC current, and to insulate multiple electrical circuits. Let's look at the transformer turns ratio, using as our example a transformer with a toroidal core. If we take the number of primary turns as N1, that of secondary turns as N2, input voltage applied to primary turns as E1, and the output voltage of secondary turns as E2, then we have this formula. And we can rewrite it like this. And if we take the current in the primary turns as I1, and that in the secondary turns as I2, we have this formula. And we can rewrite it like this. Please note that the transformer can handle AC voltage and AC current only, and that it cannot convert DC voltage and DC current. Let's now look at the voltage used for lights on board a ship. When the generator voltage is 440 volts, a voltage of 110 volts for inboard lights can be obtained by setting the ratio of primary turns to secondary turns as 4:1. The number of large-size ships offering generator voltage of 6,600 volts has been growing. A transformer turns ratio of 30:1 is employed to convert this voltage to 220 volts, which is compatible with the engine room pump. Devices that make use of semiconductors are all around us and include cellular phones, personal computers, and CD players. A variety of electronic equipment making use of semiconductor parts can also be found on board and include control panels in the control room and nautical instruments on the bridge. Let's take a look at the basics of semiconductor devices. Copper, aluminium, stainless steel, and iron exhibit low electrical resistance and therefore are effective conductors of electric current. Hence, they are known as conductors. On the other hand, the electrical resistance exhibited by glass or ceramic materials is extremely high. Such materials are known as insulators. Semiconductors have intermediate properties. Semiconductor devices have functions similar to those of a water tap. The resistance that water encounters decreases when the tap is opened, allowing a lot of water to flow out. As the tap is gradually closed, increased resistance makes it difficult for water to flow out, resulting in reduced water flow. When the tap is closed completely, resistance is at its greatest, and the flow of water stops. In semiconductor devices, the electrical signal is substituted for water, and the semiconductor functions as both a conductor and an insulator, i.e., as the tap. In short, the semiconductor device can control the flow of current. This function makes it possible to process electrical signals and convert electric power. Because of its properties, control over the semiconductor device can be lost, resulting in malfunction or breakdown. It also generates heat during use. A heat sink and fan are used to prevent the semiconductor device from overheating. To ensure the maintenance of a low ambient temperature for semiconductors, it is important to periodically check that the fan is working properly and that the panel intake filter is not blocked with dust and oil residue. Also referred to as a rectifier, the diode is a semiconductor device that works as a check valve for electrical circuits. Check valves are used in pipelines to prevent water, steam or fuel from flowing backwards and ensure that the liquid flows in one direction only. Similarly, diodes ensure that electric current flows in one direction only. A positive or negative signal is acquired using this function of the diode. It also converts alternating current into direct current. There are various types of diode. Let's look at some typical diodes. This one converts single-phase AC voltage, or three-phase AC voltage, into DC current. It is comprised of 4 or 6 diodes and has a synthetic resin cover. This is another type of diode. It is used when a high-speed operation such as DC power supply or inverter functionality is needed. Among other types of diode are the Zener diode and LED. Its advantages are low power consumption and long life. In terms of structure, transistors can be classified into 2 types, the PNP and NPN. The transistor is a semiconductor device with 3 terminals, the collector, base, and emitter. The transistor is a semiconductor device that functions like a water tap. When the amount of current IB passed to the base is altered, the flow of current between the collector and emitter also changes. This results in a change to the current IC of the collector. It becomes possible to control the large collector current IC by the small base current IB when the voltage between the collector and emitter is high. This function of the transistor is known as the amplification effect. A microphone is one example of a device that uses the amplification functionality of a transistor. Without the transistor, the sound produced by a microphone connected to a speaker is small because the electrical signal from the microphone is small. However, by adding a transistor, the electrical signal can be amplified before reaching the speaker, yielding a louder output. A thyristor is a semiconductor device that can handle a large amount of electric power. This means it is possible to use thyristors for high-voltage electrical circuits with large currents. Today, thyristors for high-voltage circuits of 12 kilovolts are available on the market. Moreover, thyristors that can handle currents as large as 5,000 amps are also available. The thyristor is also known as a semiconductor switching device. Unlike mechanical switches, thyristors have no moving parts, and thereby enjoy a long, useful life. Another feature is their fast switching speed. When pulse current is passed through the gate, the thyristor turns on. The on state is maintained once the thyristor is turned on. The current flows in the forward direction like a diode during the on state, but current does not flow in the reverse direction. To turn it off, it is necessary to reduce the current to zero, there are various ways of doing this, or by applying reverse voltage to the thyristor. Thyristors are chosen according to type of ship and application for which they will be used. Shaft power generators are widely used as devices that generate power by extracting partial power from the output shaft of the main diesel engine or steam turbines. In this shaft generating system, the frequency of the generating voltage remains unstable because the number of output shaft rotations varies according to ship speed. Thyristor inverters are used in shaft power generators to resolve this problem. When it comes to semiconductor products, including thyristors, it is important to guard against static electricity. Static electricity has a small amount of current, but the voltage can be several kilovolts or more. People are usually unaware that they have picked up electricity, making it possible for several kilovolts of static electricity to accumulate before they know it. Touching a semiconductor device in this state can cause the device to break down, a situation that can go unnoticed, since visibly it does not appear to have changed. To prevent electrostatic destruction, it is necessary to remove static electricity from the body prior to handling a semiconductor device or electronic circuit board. It is easy to rid yourself of static electricity. One simple method is to touch a tap with your bare hand. When on board ship, you can touch the steel deck, floor, or ship side for several seconds with your bare hand. However, touching an FRP wall surface or glass can actually build up static electricity. Insulated gate bipolar transistors, or IGBTs, come in various shapes and sizes depending upon the application or voltage. An IGBT is a semiconductor switching device similar to the thyristor. IGBTs turn on or off when signal voltage is input at the gate terminal. IGBTs enable a switching speed faster than that of thyristors and operate in a range from several to 10 kHz. Widely used in inverters for motor control, IGBTs are indispensable to controlling a motor's rotational speed and torque. IGBT inverter-controlled motors are often found in anchor winches and mooring winches. A metal oxide semiconductor field effect transistor, or MOSFET, is a semiconductor switching device like the IGBT. Due to a fast switching speed, MOSFETs play a vital role in enhancing the performance of power devices. For example, electronic circuit boards for communications equipment and control devices operate with a stable DC voltage. MOSFETs ensure the stable and efficient supply of DC voltage to these pieces of equipment. The mechanism by which a machine is operated step by step in accordance with prescribed procedures is known as sequence control. Many pieces of equipment operated automatically using sequence control can be found on board ships. As a simple example, there is a sequence circuit to automatically supply fuel oil to a settling tank by a fuel oil transfer pump. This sequence circuit controls the fuel oil transfer pump, stopping the pump before the fuel oil in the tank overflows, and resuming pump operation as the level of oil in the tank drops below a preset level. The motor that supplies power to the pump generates a modest amount of heat while operating. However, when the motor has been stopped, its temperature gradually begins to decrease. If the motor's temperature becomes cooler than the ambient temperature, condensation on the casing and coil could result. Condensation inside the motor can result in overcurrent, an event that takes place when insulation resistance between the coils decreases, leading to a short circuit. Reduced insulation resistance between the coil, motor, and the motor frame can also lead to electrical leakage. To prevent such accidents, an electric space heater can be installed in the motor. The space heater is off when the motor is running, and it turns on after the motor has been idle for a preset period of time. In the sequence diagram, the upper half is the main circuit supplying a three-phase electric supply of 440 volts to the motor, and the lower half is the sequence circuit controlling the power supply. Single-phase AC voltage of 110 volts is used in the sequence circuit, but in some cases, AC 440 volts or DC 12 volts is used if the location and conditions require this. The notation method is now being unified under IEC standard, but old JIS or JIS is still used. Now let's take a look at the variety of elements found in the sequence circuit. Switches and relays are classified according to operation. The three types of operation are make contact, break contact, and changeover contact. Make contact is also known as Arbeit contact, which is abbreviated as A contact or form A. If A contact is not in operation, the circuit remains open and the off state is maintained. The circuit remains closed and the on state is maintained only while A contact is in operation. Because of this, the indication NO, or normally open, will often appear on the A contact terminal. The A contact push button switch closes the circuit when the button is pressed and opens the circuit using spring force when the button is no longer being pressed. Break contact is also known as B contact or form B. If B contact is not in operation, the circuit remains closed and the on state is maintained. The circuit is closed and the off state is maintained only while B contact is in operation. Because of this, the indication NC, or normally closed, will often appear on the B contact terminal. The B contact push button switch opens the circuit when the button is pressed and closes the circuit using spring force when the button is no longer being pressed. Changeover contact is also known as C contact or form C. C contact combines the features of A contact and B contact. Prior to operation, A contact is off and B contact is on. When the switch is operated, A contact turns on and simultaneously B contact turns off. The A contactor closes and B contactor opens when the C contact push button switch is pressed, and they return to their original states when the button is no longer being pressed. Shown here is a turnover switch, a C contact with residual function. A control relay is composed of a spring, electromagnetic coil, a free-moving piece of iron, and a relay. When a current is passed in the control relay coil, the coil turns into an electromagnet and attracts the piece of iron. The relay is turned on or off by interlocking with the piece of iron. The electromagnetic power of the coil vanishes when the current passed through the coil drops to zero. Spring force returns the piece of iron to its original position. As you can see, many control relays are of the C contact or form C type. These are schematic symbols for the control relay. It is expressed as a circle in old JIS and as a rectangle in IEC standard. The number 4 indicates that the particular control relay is for use in the main control circuit. In an actual sequence circuit, the dotted line connecting the coil and relay is often omitted. The main contactor is used to turn on or off heavy load current supplied to the motor or heater. The main contactor's structure is similar to that of the control relay. It turns on when a current is passed through the built-in coil. An auxiliary relay similar to a small control relay is attached to it, and it is interlocked with the operation of the main contactor. In many cases, it is abbreviated as MC in the circuit diagram. The figure 88 is the control device number for the MC. For MCs used on ships, circuit diagrams are just as likely to be rendered in old GIS as in IEC. The relay may appear to be a capacitor at first glance, but the difference between the relay and the capacitor can be determined easily. Just look for the number 88. The timer relay is a kind of control relay. It can prolong the relay operation, but only for a set period of time. Most timer relays offer a choice of several operation modes. Chief among them are the on-delay mode and off-delay mode. In on-delay mode, the relay begins to operate when a set period of time has elapsed after current is passed through the coil. However, the moment the current passing through the coil becomes zero, the relay returns to its original state. In off-delay mode, the relay begins to operate the moment current starts flowing through the coil. However, when the current becomes zero, the relay returns to its original state once a set period of time has elapsed. The thermal relay is composed of a main circuit terminal with a built-in heater and bimetal and an auxiliary relay. It is used to intercept the circuit when the latter exceeds a certain limit. In the sequence circuit, it is possible to detect overcurrent using this auxiliary relay. The auxiliary relay will not return to its original state even if the excessive current is stopped. Therefore, it must be manually reset once the excessive current error has been resolved and safety has been confirmed. In these circuit diagrams, 51 and THR indicate thermal relays. In many cases, the thermal relay is incorporated in the MCCB and electromagnetic contactor. A variety of sensor switches are used in the sequence circuit. With sensor switches, the relay operates when the temperature, pressure, or water level reaches a preset value. A pressure switch is composed of components that detect pressure and an auxiliary relay. The relay operates when pressure rises above or falls below a set value. It is used for controlling air compressors and air conditioning compressors. With the level switch, the auxiliary relay operates when the water level in the tank rises above or falls below a certain level. There are various methods for detecting water level. In the float-type level switch, for example, the relay is operated by the vertical movement of the float. Since a limit switch is used for the relay, the level switch is often represented using the same symbol as for the limit switch in the diagram. An electrode-type level switch is also used. When multiple electrodes of varied lengths are inserted in the tank, the water level in the tank can be determined by detecting the state of the current passing through each electrode. The upper and lower limits of a tank's water level are indicated by the electrode's locations. The temperature switch relay operates when the temperature rises above a preset value. Thermistor and bimetal are often used in the temperature detection component. In some temperature switches, the relay is operated by a special liquid enclosed in the sensor that expands due to heat. In many cases, the temperature switch is represented in the circuit diagram using the same symbol as for the limit switch. Now let's look at the various devices that can be found in this sequence circuit. The molded case circuit breaker, or MCCB, is often referred to as the non-fuse breaker, NFB, or simply the breaker. The MCCB intercepts the circuit when current exceeding the rated current of the MCCB is passed through the circuit. Capable of raising or lowering AC voltage, the transformer is mainly used in the sequence circuit to reduce voltage. While this transformer is for relatively large electric power, smaller transformers are used in the sequence circuit. The fuse cuts off the electrical circuit when current exceeding a preset value flows through the circuit. The fuse protects various circuits, the main and control circuits, for example, from overcurrent. However, once a fuse is blown, it cannot be reused and must be replaced. Lamps are used to display the operational state of the motor or to display an error. LEDs are used in newer lamps. The merits of an LED include a long useful life, high luminance, and low power consumption. In cases where the sequence circuit is operated by DC and the plus and minus directions of the LED need to be clearly indicated, notations like this are sometimes used. Lamp colors are represented as abbreviations, as shown in this table. Electric motors are classified into single-phase motors operated by single-phase AC voltage and three-phase motors operated by three-phase AC voltage. While the single-phase motor is used for ventilation fans and small cooling fans, almost all motors used on ships are three-phase motors. The schematic symbol for the motor is the same in both old GIS and IEC. Fan marks and pump marks may be indicated along with the motor symbol. In the sequence control circuit, the control circuit is composed of mutually connected devices such as switches, timers, and control relays. Because of this, the circuit wiring becomes complex, making it unsuitable for complex control tasks. On the other hand, when a programmable controller is used, connecting most devices to the programmable controller will suffice, making wiring much simpler. Moreover, in some cases, only the program has to be rewritten, even when the controlling method has been changed, eliminating the need to change the wiring. As such, the programmable controller is the choice for complicated sequence control. The programmable controller is also referred to as a programmable logic controller, PLC, programmable relay, or simply sequencer. This sequence circuit, controlling the level of the fuel oil settling tank within a set range, is comprised of various devices. Its high-level and low-level switches are B-contact types, allowing the relay to open when the float rises. Now, let's take a step-by-step look at how the sequence circuit works. Let us begin by assuming that the tank is empty. At this time, the relays for the high-level and low-level float switches are closed. Let's also assume that the changeover switch for selecting auto or manual control is set to manual mode. How does the sequence circuit function under these conditions? The MCCB is turned on. As voltage is applied to the sequence circuit through the transformer, the white lamp WH illuminates, current is passed through XB, exciting the coil of the on-delay timer TLR. Here, TLR's relay operates if no operation is carried out from the time of execution till a set time has elapsed. However, here the pump is operated immediately. As the push-button switch PBSA is pressed, a current is passed from PBSA to changeover switch COS, to press-button switch PBSB, to high-level float switch LSH, and to the coil of control relay X. Thus, the coil of X is excited. As a result, XA is turned on, and the current begins to flow from XA to PBSB, LSH, and to X. Therefore, even though the finger is removed from PBSA, X continues to be excited. This state is known as the self-holding state of X. When XA is turned on, the coil of MC is excited. As MC's coil is excited, MC's contactor is turned on. Current is passed to the motor through MCCB, MC, and THR, and the motor starts. Then the pump starts operating to supply the tank with water. As XA is turned on, the green operation lamp illuminates. As XB is turned off, the timer's coil is demagnetized. As the fuel oil transfer pump usually operates in auto-control operation mode, the changeover switch is usually switched over to auto mode after confirming that pump operation has been initiated. Pump operation continues because X remains in self-holding state after switchover. If the pump operation continues, the fuel oil level rises. Here, LSH float rises and LSH relay turns off. Let's see how the sequence circuit operates from this state. When LSH relay is turned off, current passing through XA, PBSB, LSH and to X is cut off, and X coil is demagnetized. As a result, XA turns off, and X does not remain in self-holding state. MC coil is demagnetized as XA turns off. As a result, MC contactor turns off to interrupt the supply of power to the motor, bringing pump operation to a halt. As XA turns off, the green operation lamp goes out. With XB turned on, the timer TLR coil is excited. The TLR relay turns on after a set period of time elapses, and the MCSH coil is excited. Then MCSH contactor turns on, allowing current to flow to the space heater. This prevents the motor from accumulating condensation due to cooling. If the liquid level falls gradually while the pump is stopped, the LSH float goes down and the LSH relay is turned on again. However, the motor remains stopped because the X coil is not excited. If the liquid level falls even further and the LSL float also falls, the LSL relay turns on. If COS is set to auto mode, X is excited and returns to sequence operation. This is because with XA turned on, current begins to flow from XA to PBSB, LSH and to X, enabling X to remain excited even if you take your finger off PBSA. By repeating this operation, the level in the tank is controlled within the preset parameters. However, if COS remains in manual mode, the pump does not operate because X is not excited even though the LSL relay is turned on. The tank eventually becomes empty. Next, let's look at an example where the pump is stopped manually and then started again. Let's assume that the tank is about half full and the pump is operated in auto mode. At this time, LSH relay is on and the LSL relay is off. As PBSB is pressed, current passing through XA to PBSB, LSH and to X is cut, and X is demagnetized. In the subsequent sequence operation, XA turns off, and X does not remain in self-holding state, so pump operation comes to a stop. Next, let's see how pump operation is resumed. First, the changeover switch is set to manual mode. When PBSA is pressed, current passes through PBSA to COS to PBSB, LSH and to X, and X is excited. In the subsequent sequence operation, XA turns on, allowing current to flow from XA to PBSB, LSH and to X. As a result, X remains excited and pump operation continues, even if you take your finger off PBSA. Further, let's assume that current exceeding the rated current is passed to the motor during pump operation. Possible causes include the motor having stopped because of damage to a bearing, or a large quantity of dirt accumulated on the vane in the tank has caused the load on the motor to increase tremendously. Let's see sequence circuit operation under these conditions. As excess current passes to the motor, heat is generated in the thermal relay THR heater. The THR relay of the sequence circuit opens because of heat generation in the THR heater. Current is cut off as the THR relay opens and the X coil demagnetizes. Then XA turns off, demagnetizing the MC coil and turning the MC off. However, the THR relay does not reset automatically. If the relay is left as it is, the tank will become empty. This is because even though the LSL float falls along with the liquid level, the motor is not operating automatically. Make sure that the MCCB is turned off when searching for the cause of the excess current. When the problem has been resolved, turn the MCCB and THR on and start operation by switching the changeover switch to manual mode. Dust can easily accumulate inside the control panel containing the sequence control circuit. If this dust accumulates between the control relay terminal and the MC terminal, electric current may flow through it, generating heat and even fire. This fire may spread to the electric cables inside the panel and, in the worst case, burn out the whole control panel. To prevent such an incident, compressed air should be used periodically to blow away any dust that accumulates inside the control panel and switchboard. Use of cotton rags should be avoided because the oil on the rags could stick to the terminal board, making it even easier for dust to accumulate. Push-button switches, relays, and other similar devices are connected by electric cables. Vibration can cause the screws that fix the connection terminals of these cables to loosen over time. So, periodically check all screws and tighten them as necessary. All electronic equipment and apparatuses consume electric power. For example, a seawater cooling pump needs 3-phase AC voltage, while a fluorescent lamp needs single-phase AC voltage. Items inside telecommunications equipment and computers require voltages of 42 volts, 12 volts, 5 volts, and 3.3 volts DC. However, many generators installed on ships output only 440-volt 3-phase AC voltage. As such, many devices cannot directly use voltage generated by shipboard generators. Electric power conversion circuits are used to accommodate differences between the types of electric power being generated and consumed. Electric power conversion circuits perform various roles. For example, conversion from AC to DC or from DC to AC. The stepping up or stepping down of voltage. A change of frequency. And maintaining a stable voltage. The series regulator is a semiconductor device used to maintain a constant DC voltage. The series regulator can also be used to generate a steady and constant voltage. Let's illustrate the operation of the series regulator by comparing it to a water tank. The water pressure P1, available from tank 1, is proportional to water level H1 of the tank. When water pressure P2, which is less than P1, is required, an overflow pipe becomes necessary, like the one attached to tank 2. Water level H2 can be lowered to H1, and water pressure P2 from tank 2 is lowered in proportion to water level H2. Though the principle is very simple, the wastage is significant as water always flows out from the overflow pipe. Likewise, as wasteful current flows out from the ground terminal, the efficiency of the series regulator also decreases. Therefore, it cannot be used in electrical circuits requiring high power consumption. However, features such as low noise and low voltage ripple make it suitable as a power source in small electrical circuits. The DC-DC converter can step up or step down DC voltage. Because it is much more efficient than a linear regulator, it can reduce wasteful power consumption significantly. As such, the DC-DC converter has become an indispensable energy conservation solution for all kinds of electronic equipment. DC-DC power conversion devices can be classified into DC-DC converters, where input and output are insulated, and non-insulated DC choppers. Here we will discuss DC choppers. Let's use an illustrated image to explain this circuit diagram. The water level H1 of tank 1 represents input voltage V in, water level H2 of tank 2 represents output voltage V out, Water scooped out from tank 1 to tank 2 represents current I in, passing through semiconductor switch SW. Water output from tank 2 represents current consumed by load resistance R load, and movement of the person and ladle is SW plus D plus L. The buck chopper observes the water level of tank 2, or the amount of water flowing to the load, and transfers the amount of water needed to maintain specified water level H2. The buck chopper lowers the voltage and output voltage is constant. A boost chopper is used to boost DC voltage. Output DC voltage V out is obtained by stepping up input voltage V in. An IGBT and MOSFET are used as the semiconductor switch SW. Let's look at our illustration again. Unlike linear regulators, these choppers are very efficient as they do not pass waste current. The water scooping operation stands for the on and off operation of the semiconductor switch. The water scooping out speed is the chopper's switching frequency. Fluctuations in water level H2, or output voltage V out, can be reduced by making the switching frequency higher. Therefore, the chopper's switching frequency is generally high, ranging from several tens of kilohertz to several hundred kilohertz. With the chopper, input and output are not insulated. When it is necessary to do so, an insulation-type DC-DC converter is used. The insulation-type DC-DC converter can be found on the circuit board quite easily because it incorporates a pulse transformer. Inside computers, 12 volts is usually converted into 5 volts or 3.3 volts by means of an insulation-type DC-DC converter. The cooling fresh water pump, fluorescent light tube and so on are operated by 60 Hz AC voltage. However, semiconductor devices on control circuit boards and in computers are operated by DC voltage. The circuit that supplies DC power to these semiconductors is an AC-DC converter. Sometimes it is simply called a converter. For example, DC voltage is required to charge the transceiver battery. The battery charger is nothing less than an AC-DC converter. In an AC-DC converter, a power conversion circuit is configured by passive elements and semiconductor devices. Circuit configurations can be adjusted for a variety of applications. The simplest form of AC-DC converter is a rectifier composed of diodes and capacitors. While the diode rectifier can easily convert AC into DC, its output voltage VD has a large ripple and the output voltage cannot be controlled. As such, the diode rectifier cannot be used for equipment that requires a stable DC power supply. In these cases, the usual practice is to use a power conversion circuit where the diode rectifier and chopper or DC-DC converter are combined. Commonly, the large capacity aluminium electrolytic capacitor is used to remove the ripple from the diode rectification circuit's output voltage. Shown here is a three-phase AC voltage rectifier. A very simple process using an electrolytic capacitor to remove the ripple from output DC voltage makes this a popular choice. One drawback, however, is that input current is rendered as distorted waveform and not the preferred sinusoidal waveform. Not only is the power factor decreased, but because higher harmonic waves are generated when the input current is distorted, other electrical equipment may be adversely affected. The rectifiers shown here can convert AC voltage to DC voltage, but cannot control the output DC voltage value. When input three-phase AC voltage is 200 volts, for example, output DC voltage becomes something like 280 volts. On the other hand, chargers like this one are required to supply low voltage ranging from several volts to 20 volts. Moreover, since the rectifier's output voltage VD contains ripple elements, it is necessary to remove the ripple and provide a steady DC voltage. So, the actual charger incorporates a DC-DC converter like a buck chopper in addition to an AC-DC power converter. The inverter is a power converter designed to convert DC to AC. The output AC voltage is not limited to 60 Hz. The inverter can output frequency as required by the load, for instance from several hertz to 100 kilohertz. It can output not only single-phase current but three-phase current as well. What's more, the amplitude of AC current can be adjusted. The electric motor on a ship is operated by 60 Hz AC voltage, and if the load does not change, it rotates at a constant speed. The revolution speed of the electric motor can be controlled by voltage and frequency. Therefore, the inverter allows for precise control of the motor's revolution speed. Power is input as DC voltage, which is obtained by converting three-phase voltage to DC voltage via the diode rectifier circuit. Even though the inverter is used in combination with the rectifier, the system is often referred to simply as the inverter. The piece of power supply equipment known as the UPS is connected to important onboard equipment, including the main computers, communications apparatuses, and control devices. If a generator shuts down, more than a few pieces of electrical equipment will cease functioning until the power supply is restored. To prevent such an event, the UPS can provide power for a certain period of time using electricity stored in batteries. Since the battery output is DC voltage, the inverter is used to convert DC voltage to 60 Hz AC voltage. How are the conversion circuits we've seen used? Let's look at some examples. This is an example of high-voltage power supply for radar. After single-phase AC voltage has been converted to DC voltage, it is converted to high-frequency AC voltage by the inverter. The high-frequency voltage is raised to high voltage through the step-up transformer, and then adjusted for DC high-voltage output. If the frequency of supplied current is high, the transformer can be compact and lightweight. An inverter is used in the power conversion process to supply high-frequency AC voltage to the step-up transformer. A thyristor inverter may be used on ships equipped with a shaft generator. This is an outline diagram for the thyristor inverter. Three-phase AC voltage, output by a synchronous motor, is converted to DC current by the thyristor converter and DC reactor. The thyristor inverter converts this DC current to 60 Hz three-phase AC, supplying power on board. Let us now take a look at causes, effects and countermeasures in connection with power converter-related problems. As with the chopper, power converters require power semiconductor switches, such as diodes and IGBTs. The power converter converts electric power by means of semiconductor switches. However, switching may generate high-frequency electromagnetic noise. This noise is known as electromagnetic interference, or EMI. EMI has been known to superimpose the output voltage and output current of power converters, or to be emitted as electromagnetic waves from power converters, leading to control device malfunction and noise mixing in wireless equipment. Installing an electric product that contains power converters, an inverter for example, near a normally functioning temperature measuring instrument could result in erroneous display of error or overrange warnings. One possible reason for this is noise generated by the power converter entering the thermocouple. This noise is known as common mode noise. Temperature measurement can be improved by taking the following actions. If the thermocouple is covered with a stainless steel sheath, ground the sheath. If the terminal block and data logger have ground terminals, these should be grounded. Wind the thermocouple wire or its wire leads around the ferrite core several times. An inverter-controlled motor may generate shaft voltage due to common mode voltage generated by the inverter. When shaft voltage reaches the dielectric breakdown voltage of the motor bearing's oil film, bearing current will flow through the bearings and corrode them. Electric corrosion of the bearings may cause the motor to break down. It may be difficult to deal with this problem on board. Nevertheless, please keep the following in mind. Motors controlling the speed of winches and cargo pumps by inverter may have shorter useful lives. A filter circuit can be installed to prevent common mode noise. Motor control inverters always feature a rectifier. The rectifier is a kind of AC-DC converter. When stable DC voltage output is needed from the rectifier, a large aluminium electrolytic capacitor is used. In such cases, currents with high-frequency elements, known as harmonic current, may flow from the rectifier to the system side. Harmonic current is converted into voltage through the impedance of on-board wiring, the result being possible distortion of the three-phase AC voltage waveform. If the harmonic wave problem becomes serious, the transformer may begin to generate an abnormal amount of heat. Electromagnetic noise caused by the harmonic current can also enter the telephone signal line, generating acoustic noise. This problem usually occurs when the power line and the signal line are in close parallel proximity to each other. It is difficult to resolve the fundamental causes of harmonic current problems on board. However, one effective measure is to keep the transmission and signal lines away from each other. It is also advisable to confirm that the line has been properly grounded. For example, when the transmission line is covered with basket armor, grounding of the basket armor should be confirmed. When coaxial cable is used as signal wire, confirm that the armor metallic shield is properly grounded. In many cases, the part connected to the electrical equipment is grounded. Check to make sure grounding terminal screws are properly tightened. Including the inverter for motor control, most power converters use a number of electrolytic capacitors. The life of these electrolytic capacitors is short, and they deteriorate more rapidly than other electronic components used in power conversion devices. Therefore, it is no exaggeration to say that the useful life of a power converter depends upon the lifespan of the electrolytic capacitors inside it. For effective cooling of electrolytic capacitors, care should be taken so that the suction and exhaust fans of the inverter or UPS are not choked with dust or other debris. Fans should be inspected regularly to remove dust and ensure they are functioning properly. Sensors, such as thermometers and pressure gauges, are indispensable for grasping the state of various types of equipment and apparatuses and for collecting data. Here, we will discuss electronic sensors that allow you to monitor and store data in the control room. The tester is the most useful voltage measuring device for engineers. The tester measures current and voltage by directly connecting the probe to the main circuit. For the inside of a switchboard and motor starting board, voltage and current are usually measured with measuring transformers, PT and CT, by insulating and stepping down the voltage. The basic principles of PT and CT are the same as the common transformer. Based as it is on the Hall sensor, the current sensor can measure current by disconnecting and insulating and does not require a CT. This current sensor detects the magnetic field generated by the current and can measure both direct current and alternating current. This Hall sensor is used in clamp-type current sensors. Since the clamp-type sensor is built using very precise semiconductor components, this part is especially vulnerable to damage. Handle it with care. The engineer should have temperature information for fuel oil, lubricating oil, exhaust gas, seawater, fresh water, steam and air, and so on. When inspecting the engine room, temperature is measured using an analog thermometer connected directly to the piping. On the other hand, temperature data measured by electronic thermometers is collectively monitored and recorded in the control room. There are different types of temperature sensors. Here, let's look at some of them. When two types of metal wires are connected to each other at the ends and heat is passed to the contact point, voltage is generated. This phenomenon is called the Seebeck effect. The thermocouple measures the slight voltage generated due to the Seebeck effect and converts it into temperature data. The ends of some thermocouples are covered with stainless steel sheaths to strengthen the metal and protect against corrosion. The electrical resistance of metal changes with the temperature. The resistance thermometer makes use of this property. High-purity platinum wire is often used because of its heat resistance and stability. Its scope of measurement ranges from -200 degrees Celsius to +600 degrees Celsius. A thermistor exemplifies resistance where the resistance value changes according to the temperature. This property is used as a temperature sensor. A thermistor is used in air conditioners, refrigerators, heater-overheat controllers, temperature warning devices, and so on. Since the IC temperature sensor uses a semiconductor as its temperature sensor, it can be included in one IC package together with the control circuit. It is both compact and very precise. The thermostat is a device incorporating a sensor and a switch. The device is turned on or off by a contact switch set to operate at a specific temperature. While there are various types of thermostats, the disc-type bimetal thermostat is the most commonly used. Two types of thin metal plates, each with a different thermal expansion coefficient, are stuck together to form a bimetal. This deforms when heat is applied and returns to its original shape after cooling down. Expansion or reversion of the metal disc causes the switch to turn on or off. The radiation thermometer measures temperature by measuring the intensity of infrared waves, a type of electromagnetic wave radiated by the object being measured. However, since the emissivity of infrared radiation varies from substance to substance, the value derived from measurement must be corrected to ensure accuracy. When it is necessary to measure accurate temperature, it is effective to apply a black tape or black paint of known emissivity. Pressure is measured at various locations around a ship. Pressure gauges can be found in compressors, pump outlets, lubricating oil lines, and so on. In the board and tube pressure gauge, an elliptical metal tube that is flat at its cross-section is coiled in the shape of the letter C. When pressure is applied, the tip of the tube moves slightly outward. This slight displacement causes the pointer to move through a link lever gear. Pressure gauges commonly found in ships not only read indicated values, but also monitor pressure in the control room by converting the pressure into an electrical signal. When pressure is applied to a flexible disc known as the diaphragm, the disc becomes slightly deformed. The diaphragm pressure sensor converts this displacement into an electrical signal and displays it as pressure. The oxygen analyzer is an instrument used to measure combustion within the boiler. The boiler uses a forced draft fan, or FDF, to intake air for combustion. When FDF ventilation is reduced, incomplete fuel combustion occurs in the boiler, generating a large amount of dark smoke. Conversely, when ventilation exceeds recommended limits, heat loss occurs. The excess air takes heat with it as it is exhausted. Furthermore, excessive ventilation also increases NOx emissions. Proper FDF ventilation can be determined by measuring oxygen concentration in the boiler exhaust gas. The oxygen analyzer needs to be warmed up for 5 to 10 minutes before being used, so make sure to turn the analyzer on before operating the boiler. It is always necessary to know how much fuel oil remains. and whether or not the proper quantity of water has been supplied to the boiler. It is also necessary to know exactly how much crude oil or LNG has been loaded or unloaded. For these reasons, level meters are installed in most vessel tanks. The level meter is usually a glass tube connected to the side of a tank to allow for measurement by sight. The principle of the float-type level meter is to determine the level of a liquid by detecting the position of a float on the liquid's surface. Level meters vary according to manufacturer. Most float-type level meters make use of a float set inside a tank or measuring tube and then convert its position into an electrical signal. Microwaves are a kind of electric wave. Microwave level meters are so accurate that they are used for LNG and LPG tanks. But float-type level meters are also used as a backup measure. High accuracy makes the electrostatic capacity type level meter the most commonly used LNG tank level meter. This level meter can be regarded as a type of capacitor because two cylindrical electrodes are installed in the tank. The liquid's level is determined by measuring the capacitance between the two cylindrical electrodes. Pressure proportional to the product of the liquid level and the liquid density is known as the waterhead pressure, and it represents the amount of pressure at the bottom of a tank filled with liquid. Measuring waterhead pressure can tell you the amount of liquid in a given tank. This is the principle behind the pressure-type level meter. The flame detector, also known as the flame eye, is a type of optical sensor. A flame eye is installed near the nozzle of the boiler burner, monitoring the burner flame. When the burner flame is on, the flame's light passes through the sensor and is converted into an electrical signal. When the burner flame is off, the sensor ceases to produce an electrical signal. Installed close to the surface of a flywheel's turning gear, the proximity sensor measures propeller shaft revolution speed. The proximity sensor detects the presence of metal. When the flywheel rotates, grease applied to the turning gear may scatter and stick to the proximity sensor. Metal dust often gets mixed with this grease. If this happens, the proximity sensor may not work properly. To avoid this problem, when the ship is in harbour, it is advisable to wipe off any grease stuck to the proximity sensor. It is necessary to measure torque in order to calculate the ship's shaft horsepower. The output of the main engine is transmitted through the countershaft. When this takes place, the countershaft is distorted slightly. Torque can be determined by measuring the degree of distortion exhibited by the countershaft. There are several methods of calculating distortion. Here, let's look at the most frequently used methods. This is a torque meter that employs a sensor containing a special alloy. When shaft distorting force is transmitted to the sensor's length changes slightly. With this torque meter, it is possible to measure torque by detecting the slight change in the sensor's length. Another method is to detect distortion using turning gears and proximity sensors, such as tachometers. This method employs two sets of paired turning gears and proximity sensors. This method uses discrepancies in the respective sensor's output signals as the basis for calculating the value of torque. Flow meters are attached to the fuel oil line for the main engine, engine generator and boiler. Ship operating costs can be reduced by decreasing fuel consumption. This also reduces emissions of carbon dioxide, the main factor in global warming, and NOx, the main factor in acid rain. Of the various types of flow meters available, here we will focus on the oval gear flow meter. This flow meter features a pair of oval-shaped gears that are rotated by the flow of fuel oil. Fuel flow quantity is determined by measuring the number of gear rotations. The fuel oil heater is used to lower the viscosity of fuel oil supplied to the main engine from the fuel oil service tank. The viscometer is set near the fuel oil heater. It measures fuel oil viscosity and widens the steam system motor valve opening if viscosity is higher than a preset value. Conversely, it narrows the steam system motor valve opening if viscosity is lower than the set value. The transducer is used to obtain accurate data from the sensor, record it electronically, and send it to the control room. Though at first glance this may look like a terminal block, the transducer plays an important role in connecting the sensor and data logger, or sensor and electronic control device. Transducers convert data into analog signals. This data must be converted into digital format for recording, control, and display by computer, a task that is handled by analog to digital converters. This graph shows an analog signal drawn using fixed-time pulse width, a process known as sampling. Next, the heights of the sampled data are replaced with numerical values. When expressed as binary numbers, the numerical values look like this. In this way, data for temperature and pressure are converted into digital data and used in measuring devices and computers. Information is also recorded digitally on CDs and DVDs using combinations of ones and zeros. Playback of a music CD involves conversion of digital data into analog signals that are then output by a speaker. In this sense, a CD player is a digital analog converter, or DA converter. Proper use of testers makes it possible to measure voltage, current, and resistance value of electrical equipment, detect damage to the equipment quickly, and repair it. There are two types of testers, analog and digital. First, let's see how to use an analog tester. When a test lead touches the electrical equipment, the indicating needle moves according to the value of voltage or resistance of the equipment. Using the rotary switch, items to be measured can be selected from among DC voltage, DCV, AC voltage, ACV, resistance value, ohms, and DC current, DCA. A tester is used to locate defects by measuring the voltage of electrical equipment. To measure alternating current voltage, set the rotary switch to ACV. And to measure direct current voltage, set it to DCV. If the voltage range to be measured is not known in advance, set the rotary switch to the highest value in the measurement range. Make zero-level adjustments before measurement. When the red and black test leads touch each other, check if the indicating needle points to 0 volts. If the indicating needle does not point to 0 volts, adjust the needle by rotating the adjustment screws with a screwdriver. Touch the test lead to the terminal of the electrical equipment to be measured. When measuring DCV, touch the red test lead to the plus side and touch the black test lead to the minus side. If the indicating needle moves to the left side of 0 volts, the test leads have been reversed. The test leads should touch their corresponding sides. When the indicating needle moves only slightly, the measurement range is too large to be measured. In this case, make the measurement range smaller and measure again. Conversely, when the indicating needle moves all the way to the right, the measurement range is too small. In this case, the measurement range should be increased before measuring again. Frequently, a weak signal from the sensor is input in a transducer and then converted into an electrical signal of between 4 mA and 20 mA. A tester to verify the operation of the sensor and transducer can be used to measure a weak current, but not a heavy current like the one flowing through a motor. For a heavy current, a clamp meter should be used. Set the rotary switch to DCA. A measurement range of less than 30 mA suffices for measuring the sensor's output current, but when the range of the current is unknown, set the range to maximum. Make 0 level adjustments before starting current measurement. Remove terminals from the circuit and the electrical equipment whose current is to be measured, and touch the test leads in such a way that the tester is serially connected to the terminal. Approach this activity with care, because it only takes a fraction of a second to damage the tester if the test leads are allowed to touch parallel to the circuit. In the resistance thermometer, the resistance value changes according to changes in the measured temperature. The resistance value is measured by using a tester to check whether the resistance thermometer is normal or disconnected. Set the rotary switch to measurement of resistance, ohms. When the resistance value to be measured is not known, set the measurement range to minimum. Make 0 level adjustments, as in the case of voltage measurement. If the indicator needle does not point to 0 ohms, adjust the needle to 0 ohms. Failure to do so will result in an incorrect resistance value. Touch the test lead to the terminal of the device to be measured. If the indicating needle moves only slightly, increase the measurement range and then measure again. When the indicating needle moves sharply to the right, reduce the measurement range to get a more accurate measurement. Like the analog tester, the digital tester can also measure voltage, current, and resistance. A certain type of digital tester is capable of measuring AC voltage frequency, temperature, and even capacitance. As such, it is sometimes referred to as a digital multimeter. Items to be measured are selected by the rotary switch, but because in many cases range setting is done automatically, there is no need to set the range. With the digital tester shown here, measurement of voltage and resistance is automatic, but the range setting for current is manual. The test lead contact point differs only when measuring current. The precautions adopted with the analog tester should also be adopted when using a digital tester. For example, the practice of making 0 level adjustments should be followed before starting measurements. Refer to the instruction manual, because methods for making zero-level adjustments vary according to the type of tester. In the digital tester, voltage received at the test lead is converted into a digital signal, and the result is displayed as a numerical value on the display panel. If OL is displayed while measuring resistance value, the resistance of the object being measured is infinite. In other words, either the cable of the wiring or electric bulb is disconnected, or the switch is off. When OL is displayed while measuring voltage, the voltage being measured exceeds the tester's capabilities. Now let's think about how to locate defects with a tester using this circuit diagram. Here, let's assume a condition where the power source lamp does not illuminate, even when the MCCB is turned on. First, let's check the fuse. You can usually determine the state of a glass tube fuse by looking at it. If visual confirmation is not possible or is inconclusive, voltage can be measured at the output side of the fuse. Even if only one fuse is blown, voltage at the output side will be zero. In the event of a blown fuse, make sure to switch the MCCB off before removing the fuse. The resistance value of the fuse is measured by a tester. The fuse should be replaced if this value is infinite. That is, the needle is stationary in the case of an analog tester, and in the case of a digital tester, OL is displayed. In the event that cables connecting the terminal board with the white power source lamp have become disconnected, then while the MCCB is switched on, measure the voltage between the terminals of the white lamp. If the measured value is normal, the cables are not disconnected. If it is not normal, the cables may be disconnected. Switch the MCCB off, remove the cabling, and then measure the resistance at both terminals of the cables. If the resistance value is nearly zero, the cables are not disconnected. Conversely, the cables should be replaced if the resistance value is infinite. That is, the needle is stationary in the case of an analog tester, and in the case of a digital tester, OL is displayed. While the MCCB is on, measure voltage between the terminals of the lamp. If the lamp does not illuminate despite voltage being at a normal level, the lamp is damaged. The insulation resistance tester is commonly known as a mega. Electric equipment is made shockproof by covering electric cables with an insulating material like vinyl. However, since both humidity and temperature inside ships tend to be high, insulating materials are liable to deteriorate. The risk of electric shock increases if insulation resistance between the coil inside the motor and the case is reduced. As such, insulation resistance between the motor and the case should be measured at regular intervals. Here, let's see how to measure a motor's insulation resistance using a mega. Before measuring the insulation resistance, turn the MCCB off. Unless the motor is dismantled, the coil will not be visible. However, insulation resistance can be measured at the MC output terminal because the motor coil is electrically connected to the MC. So, use the mega's plus side test lead, red, to touch the MC output terminal. Use the other lead, black, to touch the ship's hull or the terminal to which the motor's ground wire is connected. Since many high-precision semiconductor instruments operate using low voltage of between 5 volts and 12 volts, they will break down if subjected to excessively high voltage. Damage usually occurs internally, making it difficult to determine from appearance alone that the semiconductor has been harmed. A mega measures insulation resistance by generating high voltage in the test lead. If a mega is used with a circuit board incorporating semiconductors, the semiconductors may be rendered unusable. Never use a mega for circuit boards incorporating semiconductors. It is possible to use a clamp meter to measure a heavy current like the one passing through the motor. Current flowing through the cables can be measured by a clamp meter without having to touch the cables. This means that current can be measured without having to turn off the equipment being checked. However, the clamp meter cannot accurately measure current flowing through basket-armored cables. Use this type of meter at parts that are free of armor. Now let's confirm the points to remember when measuring current with a clamp meter. Since the tip of the clamp meter incorporates a precision semiconductor component, never attempt to hold any object with the tip of a clamp meter or pull an electric cable with it. While measuring DC current, pay attention to the flow direction of the electric current. An arrow indicating the direction of the current is provided on the tip of the clamp meter. The arrow direction should match the direction of the current. When measuring the current flowing through the motor, note that there are 3 or 4 cables connected to the motor. Attempts to measure the current of all these cables at the same time will yield a value of 0. Measure the cables one by one. Please learn how to use the clamp meter properly to obtain accurate data.